Hello dear friends, once again, welcome back to our channel, the place where we turn complex aviation issues into easy, understandable, friendly and sweet topics. Here, we not only pick subjects that pilots want to know about, but also the ones that spark curiosity in the general public. In the near future, we are not only going to talk about the airplanes, but also about the air traffic controllers, about the airports, about the airspaces, and everything that falls inside the fascinating circle of aviation. So make sure to become part of this family, subscribe, and let's expand our wings together to fly as far as possible. Now, my friends, let's dive into today's interesting subject. Imagine you are a Boeing 737 pilot cruising along smoothly when suddenly the master caution lights come on with a single flight control light. So what's going to be the first reaction? The first reaction, in fact, will be to head straight to the flight control panel. Where is this panel? Here, maybe here, or yes, that is at captain's overhead. And you get this light, or maybe this light. Anyhow, normally the first call is checklist. But before jumping straight into the checklist, let's pause for a moment. Let's ask ourselves, what is the problem and why did it happen? You see, whenever we move any controls like the ailerons, elevators, or a rudder, we expect to feel something, a sense, a feedback that tells us yes, the flight surfaces actually moved. It's just like driving a car. When you turn the steering wheel of your car to the left or to the right, it is never super soft. You feel some resistance, and that resistance reassures you that the front wheels are responding. If a car's steering were extremely soft, even a tiny movement would cause a big deflection, and that would be dangerous. So, when we let the steering to go, the steering naturally centers itself again. So, my friends, let me to tell you that aircraft controls work in a very similar way. Let's begin with the primary flight controls. In almost all commercial jets, the primary flight controls are powered by hydraulic pressure, which is between 2,800 and 3,000 psi. So starting from the ailerons. Ailerons are small hinged control surfaces at the trailing edge of the wings, and they are located typically out on the outer sections. They control the aircraft's roll around the longitudinal axis. So when you turn the control column to the left, for example, that's very easy. So the left wing's aileron goes up, reducing lift, and the left wing proportionally moves down. And the right wing's aileron goes down, increasing the lift, and proportionally the right wing will move up. So this causes the aircraft to roll to the left. And if the aileron deflection is more than 10 degrees, the spoilers on the downgoing wing raise proportionally to augment the roll. In the Boeing 737, the control column is normally connected by the cables to the aileron field and centering mechanism. What is the function of field and centering mechanism? Or we can ask what sort of job it does for us. This system gives the pilot the sense or the feel of the control surface movement and automatically brings the control wheel back to center when released. Springs, cams, and other components all work together to generate opposing force, preventing free play and mimicking real aerodynamic feedback. Once the pilot moves the control column, he actually feels the spring tension, which is in the field and centering mechanism. He is not actually sensing the hydraulic pressure. So from there, the system connects to the aileron PCU or power control unit, and at the same time to the spoiler mixer. Coming to the rudder. The rudder is attached to the trailing edge of the vertical stabilizer and controls yaw, or the side-to-side movement of the nose of the aircraft around the vertical axis. So pilots control it with the rudder pedals. Besides controlling the side-to-side movement of the aircraft nose, the rudder plays an important function, especially in crosswind landings or when compensating for an engine failure. Just like the ailerons, the rudder has its own field and centering mechanism. It forces against spring tension so that the pilot feels a resistance, and it centers itself when the pedals are released. So when the pilot pushes on any pedal, maybe the left or maybe the right, he actually feels the spring tension, which is located at the rudder field and centering mechanism, and spring tension gives pilot an artificial feeling that the rudder has moved proportionally to the pedal movement. When we trim the rudder, what happens? When we trim the rudder, the center point shifts to the new neutral until the rudder trim is reset. And finally, the elevators. Elevators control pitch, or moving the nose of the aircraft up or down around the lateral axis. On Boeing 737, they are powered by two hydraulic systems, System A and System B. Even if one fails, the other still provides full control. The control column moves the elevators through a field and centering mechanism, same as ailerons and the rudder. And then through the field and centering mechanism, it has connection to the elevator PCU or power control unit. The field here is much more precise than for ailerons or rudder. Why? Because the system needs to protect pilots from over-pitching, which could lead to a stall. At higher speeds, the column feel heavier, requiring more force, and at lower speeds it becomes lighter, requiring lesser force to move the elevators. This variation is created by the elevator field computer, which senses the hydraulic pressure from both systems A and B, which senses the stabilizer trim position, and also senses the air speed through two pitot tubes, which are located on each side of the vertical stabilizer. Now, let's connect this to the field differential pressure light. You remember the light that we had got before. So this light comes on when there is a mismatch in pressure between the two hydraulic systems, say about 25% difference, or if there is a failure in the pitot static system. When it eliminates, the QRH or Quick Reference Handbook does not give you any checklist. It simply says continue normal operation. But here is the catch. The field you are used to won't be the same. At higher speeds, the elevators might feel smoother than usual, while at lower speeds, they may feel heavier. Everything looks normal, but in reality, during landing, if you pull with your usual force, you might not pitch the nose up enough, and that could result in a very hard landing or hard impact. So my friends, this is how pilots feel the controls of an aircraft. It's a beautiful combination of mechanics, hydraulics, and clever engineering that translate movement into feedback, letting us fly safely and with confidence. Thank you so much for staying with me through this journey. If you enjoyed this explanation, do not forget to like, share, and subscribe, because your support is the lift that keeps this channel flying higher and higher. Until next time, I wish you blue skies, smooth landings, and always safe flights. Thank you very much.
1000.
Ariana 401, wind 010 degrees 3 knots, runway 30 left, clear to land. Emirates 702, contact ground 118, small 35.
185, Emirates 702, bye-bye.